Hello, everyone. In this lesson, I'm going to talk about the polynomial and the factoring. Okay, polynomial, function, and the factoring. Okay. Obviously, you can see this is an example of a polynomial, but what's the definition of polynomial? The definition of polynomial actually has a specific representation in the function. We have seen examples, okay? We have seen examples of polynomials. And these polynomial examples are such as what? F of x equals to x. That's a polynomial. And similar examples would be f of x equals to mx plus b, which is linear polynomial. Okay, and f of x equals x will be its one of its simplest form. And quadratic function. Quadratic function is a polynomial with degree 2. So ax squared plus bx plus c, where a, we assume a is not 0. And of course, we have seen other examples of even simpler polynomial, which is f of x equals to x squared. And we know it's the rule, it's a simple polynomial. Okay. And cubic polynomial, right? Other polynomials. Polynomials, okay, such as x raised to the power 3, and or this one, power 4, etc., etc. Okay, so in general, the definition of polynomial goes like this. It says a polynomial function of degree n is a function of the form. Okay, so we're going to look at a more specific form. P of x, P is the first letter of polynomial. So P of x represents polynomial function. How does it look like? Okay, so a sub n, x to the power of n. And a sub n is called a coefficient. Okay, it's a coefficient. Okay, so we're going to have more coefficients. So a sub n. So for x raised to the power n, it has a coefficient. And the next term is a sub n minus 1, which is a coefficient for x raised to the power n minus 1. So a sub n minus 1 is a coefficient as well. So we keep going. All the way to a sub 1 of x to the power of 1. Okay, of course, x to the power of 1, we don't have to write it down. You can see the correspondence between a sub n and the degree n term. Okay, and the constant term, a sub 0. Okay, so a sub n minus 1, a sub 1, a sub 0, these are called coefficient. And here we specifically require that a sub n should not be 0. So here we have a special requirement, okay, where n is a non-negative number, a non-negative integer. Non-negative integer meaning it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Keep going, natural numbers, okay? And naturally, we're going to assume a sub n is not 0, so this is just a guarantee that the degree is n, not equal to 0. Okay, so these other numbers are called coefficients. Okay, the constant term. Okay, there's a constant term. The constant term is a sub 0, okay? It is the coefficient of x raised to the power 0 terms, right? So you can see this as x raised to the power 0. X raised to the power 0 is 1, right? And when x is not 0, so constant term. Okay, constant term. And a sub n has a name, has a very special name. So a sub n has a very special name. Its name is leading coefficient. Okay, leading coefficient. Leading coefficient. Okay, so that's about the definition of polynomial. Now in this example, in the example as follows, we can see we have the highest degree is 4, right? So we will have a sub 4, a sub, okay, so we have a sub 4, which is a coefficient, is the leading coefficient. Its value is equals to 1. Okay, and what is a sub 3? A sub 3 is the coefficient for x raised to the power 3. It is equals to -2. And a sub 2 is the coefficient of x squared term is -2. And a sub 1 is the coefficient for x to the power 1 term, which is also -2. And the constant term is a sub 0, which is equals to -3. Okay, and that is the constant term. That's the constant. Okay. Now, what are we concerned about a polynomial function? In this topic, of course, we're going to talk about factoring specifically. Okay, we're talking about factoring specifically. For factoring, there are a couple of theorems we're going to talk about. And before we do that, we're going to, review some of those concepts. Okay. 0 of a polynomial. Okay. 0 of a polynomial. 0 of a polynomial. What is the definition of 0 of polynomial? Okay. If a number C, okay, we'll plug in we'll plug in the C into the polynomial. P of C equals to 0. Okay, so C as an input that will cause the output of the function equals to 0. Okay, C as the input to the polynomial, and the output is 0. When this happens, C is called a 0, is a 0 of the polynomial. Example. Okay, for example, suppose I have a polynomial which is equals to x squared minus x minus 2. Okay, and then if I substitute, say, 1, -1, sorry, -1. Okay, so I plug in -1. When I plug in -1, and x will be replaced by -1, to see that works. Okay, and another -1 minus -1, and then we're going to evaluate. -1 squared is +1, minus -1 is +1, and minus 2, that equals to 0. So the input -1 make the polynomial's output value equals to 0. Then we say -1 is a 0 of this particular polynomial. So that's the definition of 0 of polynomial. Okay. Now, there's some interesting relationship. Okay, relationship between 0 of a polynomial and the factor of a polynomial. Okay, in algebra, we spend a lot of time to factor polynomial, all kinds of polynomial. Okay, I'm sure you have experience doing that. What's the relationship of a 0 of a polynomial? Okay, 0 of a polynomial and a factor of polynomial. So I'm going to put A0, right? A0 of a polynomial and a factor of a polynomial. What's that relationship? Okay, in the previous example, right, we know that -1 is 0 of this polynomial. On the other hand, if we factor, okay, for example, okay, if we factor the previous polynomial, we're getting x plus 1 times x minus 2. Okay, and it looks like plus -1 is 0 of the polynomial, and x plus 1 is a factor of the polynomial. That is the relationship. Okay, is this relationship true always? The answer is yes. It's been proved. So we're not going to prove it, so we're just going to enjoy the result. Okay, so here we're going to have the following: real 0 of polynomials. Okay, if a polynomial, if P is a polynomial, okay, and C is a real number, then the following statement are equivalent. Following statements are equivalent. The first one, C is a zero of a polynomial. C is a zero of a P of X of the polynomial. Okay? i.e., that is P of C is equal to 0. Second, okay? Second, if one is true, then X equals to C is a solution to the equation of P of X equals to 0. Okay, and of course that is implied in the definition of 0, right? And when we solve the equation of P of X equal to 0, we're finding the zeros, okay? And from the zeros, we can identify the x-intercepts, right? That's the geometric meaning. So I'm going to give you examples after all these statements are done, okay? 3, X minus C is a factor. X minus C is a factor of P of X. Okay? And what does that mean? What does that mean? If we divide P of X by X minus C, okay, in other words, if we divide P of X, okay, we will elaborate on this one, but this is a very useful piece. We're going to get a quotient. Okay, we're going to get a quotient. And this quotient, okay, we're going to get a quotient. And the remainder from that division is going to be 0. Okay, remainder is going to be 0. Okay, this part will be elaborated. This is just, done in long division. Number 4, C is an x-intercept. C is an x-intercept. Okay, I would say C comma 0. Okay, C comma 0 is an x-intercept of the graph of P of X. To illustrate this, we're going to use that example. This is quadratic. Okay, we're going to use this example, this function. Okay, we're going to use this function as an example. Of course, all of these has been proved theoretically very thoroughly. Okay, we use the example to illustrate because we want you to understand what it means. And so, but here we're not going to do the proof. And the proof, you can be assured that the proof is rigorously done. Okay, so we have this function. And now the first thing we did was P of, in our case, we have, if we've chosen C equals to -1, right? We have done P of -1 equals to 0, right? The first one. That's equal to 0. Number 2, if we solve the equation, right? If we solve P of X, right? If we solve for X right? By setting P of X equal to 0, oops, P of X equal to 0, and we solve for X, we are getting, you can use a quadratic formula, factoring, or completing square. So here we use X factoring. Okay, so we're gonna get X equals to X plus 1 equals to 0, or X equals to X minus 2 equals to 0. And so in the end, we get X equals to -1, or X equals to 2. You can see we also found another C which has plays similar role as C equals to -1, number 2. Number 3, you can see that X minus C is a factor. Well, that has been done, right? We have factored it. So X minus C is a factor, right? X, what is X minus C in this case? X minus C in this case is X minus C is -1, right? X minus -1 is equals to X plus 1. X plus 1 is indeed is a factor of P, right? We factor it, we have one of the factors, which is X plus 1. Number 4, C comma 0, so -1 comma 0 is what? Is an x-intercept of this set function that in this particular example. And from the graph, we can see that very clearly. From that graph, we can see this very clearly. Okay, so I'm going to borrow this, the software to do this graph. I'm just making some adjustment here. Okay, so you look at the graph. Okay, so that's then we are going to just make some adjustments. Okay, and the -1, 0 is right here. You can see that's the one of the x-intercepts. That's one of the x-intercepts. Okay, so I'm going to point it out to you. -1, 0. I will make it a red dot. Oops, how come it doesn't turn red? That's why. Okay, that's one of the 0. So that's number 1, 2, 3, 4. Okay, confirmed. That's an example. And we can see the same thing about 2. Okay, we can say the same thing about 2. What about 2? Okay, P of 2 is 0, right? And solve for, we get X equals 2, X minus 2 is a factor, and 2 comma 0 is also a, we can repeat everything all over again. Okay, we can repeat everything, but this time it's going to be C equals to 2. Okay, so let me just quickly repeat that for your exercise. Okay, for your exercise. You can pause it and try this yourself. So for C equals to 2, we also have C equals to 2. That's going to be 0, right? So that's going to be 2 minus 2, and that's going to be 0. Okay, and solve for X, we get X equals to 2, and X minus 2, right? That's X minus 2 is indeed a factor, and 2 comma 0 is also an x-intercept of the curve. So I'm going to mark the other point, which is another red dot, which is also x-intercept. Okay, so that's the that is the conclusion. Okay, what it means that we have 0 or a factor, right? 0 or the other factor. Now, there's another interesting theorem where you're going to also learn it in calculus, which we call an intermediate value. Intermediate value theorem. For polynomials. What it says is that if a polynomial, if P is a polynomial, okay, and we choose numbers A and B, okay, so P of A, okay, you choose a number A and you choose a number B, and P of B are opposite in sign. Opposite in signs means one is a positive, the other one is a negative. And the other one is negative, the other one is positive. Then there exists at least one value, 10. Okay, at least of one value C. Okay, and C is between A and B. Okay, between, okay, the C is between A and B. Whoops. Between A and B. Such that P of C is 0. Okay, so I'm going to make it a little shorter. Okay, what does that mean? What does that mean? Okay. Take another example. Okay, we've been using this example too many times. We've been using this example too many times. Let's take another example. I'm going to take this example over here. I'm going to take this example over here. Okay, example. Okay, so I'm going to arbitrarily choose two numbers. Okay, for example, I'm going to choose P of 2. Say -2. Okay, I'm choosing numbers randomly. Okay, so I'm going to choose A equals to -2. And P of -2 equals to, so I'm going to plug in the -2 in this function. So that's -2. Oops. Wait. P of -2. Okay, P of -2. P of -2, so here is going to be x replaced by -2, x will be replaced by -2. Okay, so every x is replaced by -2. Every x replaced by -2. What do I get? Okay, so we're going to evaluate it. Okay, just be patient. Okay, so you understand the process. P of -2, -2 to the power 4 is -2 times -2 times -2 times -2, 4 times, so that's 16. And -2 times -2 to the power 3, and that's another 16, so plus 16. And over here, -2 times +4, so that's -8, right? And -2 times -2, that's a +4, and that's -3. Okay, so we get we just get to do the arithmetic, right? 32. So this will make 8, right? 16 plus 8 is 24. Okay. This is 8 plus 16, that's 24 plus 1. Okay, 4 minus 3 is 1. So this is 25. This is 25. Okay, so I get a positive number. So I'm going to choose another number, b equals to, say, 3. Why not? Right? Totally random. We're just illustrating this intermediate value theorem. Okay, so I blindly just choose any two numbers, a, b, and plug in and see what I get. And obviously, you see, you wish that we have some kind of guideline to choose those numbers, right? So now keep the choose 3, no big deal, right? So we're going to just choose the x equals to 3. Okay, choose x equals to 3. I'm just going to quickly double check if I get the right number. 25, that was good. Okay, and plug in the numbers over here. That's going to be 81, 3 to the power 4, that's 81, minus 2 times 3 to the power 3, 27. So 2 times 27 is 54. Minus 2 times 9, that's 18, right? 18. Minus 6, minus 3. So minus 6, minus 3. Okay. What do we get? It looks like we're going to get a positive number, right? So 81 minus 54 and minus 18. So all of these together, what do we get? We actually get a 0. Isn't that interesting? No problem. No problem. So can we apply the theorem now? Can we apply the theorem? Oops. Can we apply this theorem right here? Intermediate value theorem for polynomial. The answer is no. The answer is no. We cannot, right? Because P of A is -2. P of A is positive. But P of B is not the opposite sign. Okay? They're not opposite in sign. Therefore, in this case, this theorem does not apply because P of A and P of B are not opposite in sign. P of B is 0 because if P of A is positive, if P of B is negative, then we can apply. We can apply. Okay, but no big deal. Let's try another case. You can also see how, this trial and error process can be. I still keep this A equals 2. I'm going to choose -1. How about that? Right? -1. -1. Right? That's for the fun of it. No problem. And now all of these is going to be redone. P of -1. So what do I get here? -1 to the power 4 is 1 minus 2 times -1. So this is going to be -1. -1 times -2 is positive 2. Minus 2 times -1 squared. So this is going to be -2. Right? And this is going to be positive 2 minus 3. Positive 2 minus 3. So what do we get in the end? We get 0. We get 0. All right. So no problem. Okay. But in both cases, we cannot apply the theorem. In both cases, we cannot apply the theorem. But we actually found 2 zeros. Okay, we found two zeros. That's interesting. That's great. But it's okay. We're going to find a case where this applies. Okay, so we're gonna choose another pair of A, B. Okay, so what I'm going to do is I'm going to choose f of -2 is chosen. Okay, I'm going to choose, for the next example, I'm going to choose this one. Okay, I'm going to put it on the top. Okay, but this time I'm going to choose my B equals to 0. How about that? So what is B of 0 equal to? B of 0, B of 0, B of 0, of course, equals to -3. This time the theorem applies. So what do we mean here? You can see, okay, read the statement of the theorem. P of -2, okay, and the P of 0, okay. The former equals 25, the latter equals to -3. 25 and -3 are opposite in sign, Thus, okay, according to the theorem, there exists at least one value C between, then there exists at least one value C between A and B. Between A and B, A of course is -2, B is 0, such that P of C equals to 0. And of course, we already found it, right? What is it? What is it? Oh, actually, we didn't find it, sorry. So between -2 and 0, okay, so basically, we see this situation, okay? P of -2 is 25, P of 0 equals to -3. So if we put these on the dots, right? So from -2 to 25, right? There's one point here, that's P of -2 equal 25. The other point is 0, -3. So now if we put these in the picture about the graph, what are we going to see? Okay, we're going to plot these 2 points together in the picture. Okay, so -225, -225. I'm going to make it a red dot. And the other point is 0, -3. We have two dots. Okay. So let's -5, +5. So here we're gonna make it a -5, 30. So the curve is going to either going this way, right? From one point to the other, they're gonna have to cross the x-axis. Okay, it's gonna have to cross the x-axis. So the curve will have to cross the x-axis. Okay, in that regard, so if we graph this curve, right, you're gonna see these two red dots will be passed. And along the way, the curve is going to cross the x-axis. And that crossing is -1, luckily. We found a 0. So what the theorem says, when you have a positive function value, a negative function value. Okay, so let me just make a little bit adjustment to that picture so you can see it, a nicer picture. Okay, still not complete. How about that? Okay. Between these two red dots, okay, the curve will have to cross the x-axis from positive to negative. So that's intermediate value theorem is saying. Okay, and of course, you can see finding these two values is actually by trial and error. But with modern technology, actually, that's not very difficult. You just plot points. Okay, So that's intermediate value theorem. You're going to learn another version of intermediate value theorem in your calculus class. All right, so we have studied all of these properties, okay, about zero factor of polynomials. And next, we're going to talk about how do we identify zeros? Because we know if we can find zeros, then we can find factors. Okay, and this will take us to study this next theorem. We call it rational zero theorem. Rational zero theorem. Rational zero theorem states, okay, if the polynomial, okay, I'm going to borrow the notation we had before, okay, if the polynomial is just like that, right, we have that polynomial. We have that polynomial. So that's how polynomial look like. That's integer coefficients. Okay, integer coefficients. All the coefficients are integers. Okay, leading coefficients integer. All the coefficients are integers. The constant term is a0, right? And we assume not on a sub n is not equal to 0. We assume the constant is not 0 as well. And then, okay, and here's the conclusion, right? So if this is the condition, and now is a condition. This is the conclusion. Then, okay, every rational zero, every rational zero of P of X is of the following form. If of the form P over Q, P over Q. Isn't that interesting? Then of course we're gonna be explained what is P and what is Q. Okay, so that is the form. Okay, and now we're going to explain what is P, what is Q, where P is a factor is a factor of the constant coefficient a sub 0. Okay, and Q is a factor of the leading coefficient of the leading coefficient a sub n. A sub n, what does that mean? What does that mean? Okay, so we're going to give two examples here. Example number 1, okay. Take the example of, say, find the rational zero. By the way, do you guys know what is a rational zero? Rational means rational number. Okay, rational number basically are fractions. Okay, rational zeros are any zero that is a fraction. That's what it means. Okay, so rational zero basically means this is a rational number, okay, where P and Q are both okay, P and Q are integers. Okay, rational number. Let's take this example, okay? Find the rational zeros. Okay, of this function, polynomial function, which is x raised to the power 3 minus 3x minus plus 2. So we're going to apply rational zero theorem. We're going to apply rational zero theorem. Okay. So first we have to find all possible form of P over Q. That means we're going to factor the constant term and factor the leading coefficient term. So what is the leading coefficient term? Here we have power 3, so the leading term, the leading coefficient is a sub 3. A sub 3. Okay, a sub 3 is 1. Okay, what are the factors? Its factors are just positive 1 or negative 1. And what is a constant coefficient? Which is a sub 0. A sub 0, right? A sub 0 equals to the positive 2. So what are the factors? Right, the factors will be plus 1 minus 1, plus 2 minus 2. So we are making, so all of these are candidates for what? For Q. And all of these are candidates for P. Okay, so how many possible P and Q, P over Q we can we make? Okay, how many possible P over Q we can make? So we're going to make P over Q. Okay. So for each possible P, each possible Q, right? So we're going to make those composition. So in the end, we get positive, negative 1, positive, negative 2. Okay. So we have 4 possible. So if there are any rational zeros, okay, according to the rational zero theorem, okay, the rational, according to rational zero theorem, that every rational zero will be of this form, right? So we have all possible cases. We're going to try, okay? We're going to try, we're going to test it. We're going to test it. So we're going to plug in all of these numbers, okay? So P of negative 1, P of positive 1, and P of negative 2, and P of positive 2. Okay, so let's roll up our sleeves and do this operation. So plug in negative 1, x replaced by negative 1, x replaced by negative 1. Oops. Okay, and we evaluate it. And we got 4. No, that doesn't make it equal to 0. So for 1, replace x by 1, and we got a 0. Yay. Replace x by negative 2. Oops, sorry. Negative 2. Okay, replace x by negative 2. And we evaluate. So what do we get? Whoops. Oh, sorry. Negative 2. My bad. Oh, we got another 0. 2. 3 times 2. Great. We got 2 rational zeros. Okay, so we got rational zeros are, in this case, we have 2, c equals to 1, c equals to -2. We got 2 rational zeros. Okay, so this is how we apply rational zeros. Okay, by trial and error. But once we find these rational zeros, what do we do with them? Okay, so let's look at another example. Example number 2. Okay, so this time I'm going to use the other example right here. Right, this time is degree 4. And we're going to do the same thing. Find the rational zeros. If you like, you may like to just take a pause. Okay, try on your own. Okay, so what is the leading coefficient? The leading coefficient here, we have a sub 4. Right, we have leading coefficient a sub 4. That's going to be equals to 1. What are its factors? The factors are positive 1, negative 1. Okay, so these are the candidates for what? For Q. These are the candidates for Q. Okay, how about the constant coefficient? The constant coefficient here we have is equals to what? -3. What are the factors of -3? The factors of -3 is plus minus 1, plus minus 3. And what are the candidates for P? These are the candidates for P. So now let's look at all possible values by doing P over Q. What do we get? Right, so we're going to take plus 1 minus 1 divided by plus 1 minus 1. So we have plus 1 minus 1 and plus 3 minus 3. We have 4 candidates for rational zero. And so what do? We're going to plug in. Okay, we're going to plug in with -1, positive 1. We're going to plug in with -3. And we're going to plug in with positive 3. Oops, positive 3. Okay, so we're going to plug in 1 at a time. Okay, x replaced by -1, replaced by -1. Okay, and this is replaced by 1. Replaced by 1. Replaced by 1. Okay, so 1 by 1, we're going to evaluate. Oh, we got a 0. We got -8. That's not 0. So -3 will be replacing x. One more time. Another time. And one more time. So now we can evaluate when -3 is plugged in. We got 120. That doesn't make 0. So -3 is not a 0. So now replace x by 3. Replace x by 3. Replace x by 3. What do we get here? We get 0 again. Wonderful. So what are the rational zeros we have? The rational zeros we have here are c equals to -1 and c equals to positive 3. Wonderful. So once we get to this place, okay, once we get to this place, suppose we want to thoroughly factor this polynomial. What do we do? What do we do? Because now we know we have 2 factors for a given polynomial. We have 2 factors for a given polynomial. What do we do from there? Right? In the previous example, right? So we get two factors for this polynomial. Okay, so let's go back to example number 1. So we do that simple example, see what you can do. Okay, so for the first example, we get two factors, right? Because these are two zeros, so we got two factors. These two factors are x minus 1 and x plus 2. Okay, and what do we do then? Right, we're going to take this polynomial and we're going to do long division. We can do long division 1 by 1, or we can do long division all at once. Okay. If we do it 1 by 1, you can do long division. You can also do synthetic division. I'm going to talk about long division here because I think long division is more general. Synthetic division only works for when divisor is linear. So we're going to do long division. So if our goal is to factor the polynomial completely, what are we getting? Right, if we factor the polynomial completely. So we're going to take this piece, okay, and we're going to divide this by p of x by one of the factors. Okay, by one of the factors, x minus 1 or x plus 2. You can pick either one of them. So I'm going to pick x minus 1 to see what do we get. Okay, so we're going to do step by step. Long division set up. Okay, so here's the divisor. Okay, and over here, I'm going to, oops. Oh, that's okay. I'm going to do it this way. Yeah, it's a little bit awkward to set up. It's much easier to write it on the board, but it's okay. We can do it. Okay, so I'm going to do this way, x minus 1. And over here, so that's going to be like that. Okay, separate it. So now I'm going to have x raised to the power 3. And remember, we have x squared term missing. Okay, so that's going to be 0 times x squared term. Okay, so we start our long division. So we're going to pick a number on the top. Okay, so that's going to be x squared. Okay, x squared times x equals to x raised to the power 3. And x squared times negative 1, that's going to be minus x squared. Okay, and then we're going to the top row subtracting the bottom row. So like terms subtracting each other. X raised to the power 3 subtracting x raised to the power 3, that's going to make 0. So this is going to be 0. Okay, that's going to be 0. And 0 times x squared minus negative x squared, be careful. 0 minus negative x squared, that's going to be x squared. It's turn into positive x squared. Okay, that's what I wish you to understand. Okay, 0 minus negative x squared. Okay, and these p's subtract 0, so they're going to come along. They come along. Okay, And next we're gonna choose, that's like doing division, okay? Next one, I'm gonna choose x. So x times x equals to x squared. Okay, and x times -1, that's minus x. So once again, we're gonna do top minus bottom. Top minus the bottom. X squared minus x squared, that makes 0. Okay, -3x minus negative x. Okay, -3x minus negative x is going to be minus 2x. And of course, we bring down the 2, one last time. We're going to choose a -2. -2 times x, that's going to be equals to -2x. And -2 times -1, that's a +2. And top subtract the bottom. Top subtract the bottom. And this time we're going to get 0 as remainder. 0 as remainder. Okay, so this is a long division. Okay. Once it is done, okay, we're going to make a composition. Okay. The function, okay, p of x. Okay. Divided by, this is divided by the divisor, which is x minus 1. Okay, so let me put one more thing in front of it so you guys get more familiar. So p of x, okay, so p of x divided by x minus 1. I'm going to make the font just a little bit larger, okay, equals to quotient plus remainder divided by divisor, okay, divisor, which is x minus 1. In this case, what is a quotient? This piece is called dividend, okay? So this piece is called a dividend. So I'm going to, okay, that's called a dividend. And x minus 1 is called a divisor, okay? So where do I write divisor? Okay, I'm going to do it here, okay? Divisor. So this piece is called divisor here. There, divisor. Okay, so x minus 1 is divisor. And this piece is called quotient. Okay, quotient. Okay, you need to learn how to compose these. Okay, so this piece is called quotient, divisor, dividend. And the last one we got here is called remainder. Okay, so after we've done the long division, after we're done with the long division, what we're getting here is we're going to put a quotient in the place where quotient belongs. Okay, so quotient goes here. Remainder here, we got a 0, right? And 0 divided x by minus 1 is going to be 0. So in the end, what are we getting? We're getting this piece. 0 divided by that, that's going to be just 0. Okay? With that done, Oh, I think I should keep it. Okay, so I should keep that other form. Okay, dividend. So I'm going to give you some time to reflect. Okay, divisor is equal to quotient plus another fraction form, okay, where divisor, sorry, and remainder. Okay, make sure you understand this form. Okay, make sure you understand this form. Very important form. You're going to get to use this in calculus as well. There, so I boxed it. Okay, the consequence of what we have done for this example after long division by the factor, by one of the identified factor, is that we get this form, right? Once we get this form, we can multiply both sides by x minus 1. Okay, so we multiply both sides by x minus 1. And this other side, we're going to multiply by x minus 1. Of course, x cannot be equal to 1 in this case, right? So in the end, we get the original p of x is going to be equal to x minus 1 times that. You can put this in the front, doesn't matter. Okay, so p of x eventually is factored in that form. You can continue to do long division on x squared plus x minus 2, or here, the factoring is already pretty obvious. You don't need to do that. To completely factor, you just have to do x minus 1, and here, the next one, you're going to get x plus 2 times x plus 2 times x minus 1. Okay, so in the end, we actually get that the factors are, we have multiplicity for x minus 1, just, the multiplicity is 2, and the factor of x plus 2. You're finished. We're finished. Okay, and next we're going to look at example number 2. We're going to do similar things for example number 2. Of course, the degree is higher. Okay. You may like to pause here to try your own. Okay, we're going to continue on working on example number 2. It's similar to what we did before, right? We have identified some interesting rational zeros. So what we can do this time, I'm going to give you the example of doing long division. But this time, I'm going to make it a factor because we know we have 2 factors, right? We have 2 factors. So these 2 factors are, one is x plus 1, and the other one is x minus 3. Okay, so we're going to take these 2 factors. I'm expanding this, right? We're going to FOIL this. I'm going to take this thing to divide into the given polynomials. I'm going to do this long division. So this long division is going to be done in the following way. Okay, so this is the dividend. Okay. And we're going to set up the long division. That's set up my long division. And my divisor. Okay. My divisor. So I'm going to use a dark color. My divisor is going to be x squared minus 2x minus 3. Okay, so divisor is right here. Okay, and my quotient is going to be on the top. Okay, so now the first one I'm going to choose x squared. X squared times x squared equals to x raised to the power 4. Okay, x squared times negative 2x, that's going to be negative 2x to the power 3. Okay, x squared times negative 3 is going to be minus 3x squared. And then we're going to do subtraction. The top row subtracting the bottom row. Okay, so the top subtracting the bottom. So like terms subtracting each other. Okay, so that subtraction sign is invisible, but it's in your mind. So x minus x to the power 4 minus x to the power 4, and that is going to be 0. Oops, 0. Negative 2x to the power 3 minus negative 2x to the power 3, that's going to be another 0. Okay, negative 2x squared minus negative 3x squared. Okay, in your mind, I want you guys to do this. Okay, negative 2x squared, which is on the top. Subtracting, sorry, negative 2x to the power 2, negative 2x squared minus negative 3x squared. So the top minus the bottom. Okay, that's what's going on this step. Okay, so that's going to turn into negative 2x squared plus. Okay, so that's going to turn to plus. So that's going to make x squared. So x squared is going to be down here. Okay. Now, the other two subtracting zeros, we just bring them down. We just bring them down. Okay. And for all of these zeros, we can just ignore them. If you like to keep the integrity and make it look nice and pretty, you keep it this way. Okay. And next, we're going to add 1. We're going to add 1. 1 times x squared equals to x squared. Okay. 1 times negative 2x is negative 2x. 1 times negative 3 is minus 3. And now we're subtracting the top by the bottom. And obviously the top and bottom are the same. And the remainder is 0. So this long division is done. Okay. Once this long division is done, okay, I'm going to bring back this piece. Okay, we're going to review what's been done. Right, we're going to use this form to compose our final, bring our conclusion together. Right, so we have quotient. Okay, so this is a quotient. And of course, that is dividend. After that long division is done, we can follow this, the same formula that to establish the relationship between the dividend over divisor. Okay, over the divisor, our divisor is x squared minus 2x minus 3. Okay, you can see I do this too. You can see I do these two examples slightly differently, is that you can do the way in each case in different ways. depends on how much information you get about the divisor, about the rational zero. Okay, so here, of course, our factors are x plus 1 times x minus 3. So we can choose our divisor this way. And the quotient, our quotient is x squared plus 1, which looks really neat, right? We're lucky. And the divisor is, you can use either one because they are the same. They are the same. Okay, you can use either one. They're the same thing. And remainder is 0, right? So this piece is just gone. Okay, so in the next step, we're going to drop the 0. Okay, 0 is omitted. And then what do we get here? Okay, what do we get here? If we multiply both sides by the denominator, okay, we're going to get a p of x, which is the original dividend. And that is equal to, when we multiply the divisor on both sides, okay, that's going to be equal to that divisor multiply the quotient. The quotient is x squared plus 1. Okay, it is factored. It is factored almost. Okay, can we factor this further? The answer is yes. The answer is yes. Actually, let's put in all the factors we got, right? We're going to replace this piece by our factored form we got, right? Which is x plus 1 times x minus 3 and times x squared plus 1. The question is, can we factor this further? The answer is depends. Okay, the answer is depends whether you want to factor this in real number you want to factor this in complex number. Okay, in real number, if the factors are all in real numbers, then we are actually done. If we want to factor in complex number, then we can factor further. So next, I like to introduce to you the fundamental theorem of algebra. The fundamental theorem of algebra. Okay, so here we have a couple of conclusions here. Okay, of course, we're not going to prove it, and we're going to enjoy the conclusion. We're going to come back to this example to see what will be look like, right? Fundamental theorem of algebra. Okay, it's in your calculus class, you will learn the fundamental theorem of calculus. Okay, it's a very, very important theorem. And now we're in algebra, we have a fundamental theorem of algebra. From that title, you can see it's a very, very important result. Okay, a fundamental theorem of algebra says every polynomial, okay, every polynomial okay, so I'm going to borrow from what we did before, right? Every polynomial like this, okay, we're going to have to specify what kind of coefficients, right? An is the leading coefficient. So here we have some special requirement, very basic requirement, which is n is greater than or equals to 1. Okay, so it's not a constant. And the leading coefficient is not 0. To guarantee that the degree is at least 1. Okay, so every polynomial with a complex coefficient has at least one complex zero. Has at least one complex zero. So the zero may be complex numbers. Okay, and of course, our previous example, this polynomial, right? It has a real number coefficient, and if we have real numbers are also complex numbers. Okay, real numbers are complex numbers. Okay, we don't need that. So real number are complex numbers. So in that regard, okay, hold on. What I'm trying to do is I'm just trying to write it down in this form. So we just need that. Okay, from this example, you see it has at least 1 0. Any real zero is a complex zero, right? So this theorem certainly applied that, and this example definitely confirmed. It's not a proof, but as a verified that conclusion. Fundamental theorem of algebra. This is it. If we apply fundamental theorem of algebra n times, okay, once we get a 1 complex zero, second time we get a complex zero. So what happens is that we keep applying this fundamental theorem of algebra for n at least 1, so we would naturally get the following conclusion. It is called a complex or complete factorization theorem. In our algebraic study experience, we have spent a lot of time factoring polynomials. If you look back, okay, if we look back to our previous experience, we have done a lot of it. We've done a lot of it. Sometimes it can be factored easily. Sometimes it cannot be factored easily. But we always wonder, can we actually factor these? Well, theoretically, it has been proved that every polynomial can be factored. Okay, so this is the result. Okay, if p of x is a polynomial, of degree n greater than or equals to 1. The degree is at least 1. Then there exists complex numbers. And what are these complex numbers? Okay, so here are the complex numbers. Complex number A, C sub 1, C sub 2, and all the way to C sub n. Notice that this n and the degree n are consistent. In other words, degree n, we will have n complex numbers such that, okay, so here A is not 0. Well, if A is 0, then the whole thing is 0, right? So that assumption is completely natural. And we will be able to rewrite this polynomial as follows. A times X minus C sub 1. So one factor, another factor, C sub 2, all the way to X minus C sub n. So every polynomial can be factored. And if this applies to complex polynomials, and for real number polynomial, it certainly applies too. However, okay, sometimes we may have multiple factors. That's okay. We have those multiple factors will be, the factors with the multiplicity will also be counted. Okay, so it still is consistent with complete factorization. Okay, now, if we have some special requirement, right? Before we talk about that special requirement, obviously we haven't finished the factoring, right? So in our previous example, according to complete factorization theorem and the fundamental theorem of algebra, we are not done, right? So now return to example number 2. Let's factor it completely, right? Because we know that every such polynomial with degree 4 can be factored into 4 factors. We only have 3. And here we have a degree 2. So we must be able to factor this one. So how do we factor this one? We can use, what can we use here? Well, we can use that 0, right? If we can find the 0 of x squared plus 1, then we will be able to find the factors, right? So we're going to set, whoopsie. Sorry. So that's going to be x. I'm going to return that x squared plus 1. So what we're going to do is that we're going to take this part and we're going to find the 0, right? So we're going to find zeros for what? For x squared plus 1. We find zeros for x squared plus 1. We set it equal to 0, right? And then we get x squared equals to -1, which is I. No, sorry. We take square root. Okay, we take square root on both sides, and then we got I. Okay. Oops. What I'm trying to do. Okay, come here. This equals to. I think I'm just a little bit tired. So I'm going to take square root on both sides. On the right-hand side, it is I. Okay. And the left-hand side is absolute value of x equals to I. As a result, x equals to plus I or minus I. And of course, here you can also use the quadratic formula. You can also use the quadratic formula, okay? But I just find it easier to use this one because we have a perfect square here, okay? So now what are the factors? What are the factors for x squared plus 1? Right, because 0 and factors are related, right? We studied this earlier. Let me bring that up. Okay, so to refresh. Right here. Right, so we're going to apply this piece. This is for real 0. Does it work for complex 0? Yes, it does. It works for complex 0 as well. Okay, so with that in mind, we get 2 other factors. And these two factors are x minus I and x plus I. Okay? And if you FOIL the right-hand side, you're going to get exactly the left-hand side. So finally, for that example we did earlier, we got a complete factorization, which is x squared plus 1 is going to be replaced by that complete factorization. This is not a proof, but definitely verify that for this particular polynomial, it can be completely factorized. It can be completely factored. And in the factors, we have complex numbers. Okay, we have to deal with complex numbers. Another interesting phenomenon I want you guys to notice that the polynomial we study here is all real number coefficients. In its complex factors, okay, we got some real factors, we got some complex factors, but the complex factors, it looks like they have their conjugates. So we wonder, is that true all the time, or is it just true this time? And this will lead us to another result. Okay, it's called a conjugate zero theorem. What is a conjugate zero theorem? Okay, so once again, if a polynomial of degrees n at least 1, okay, we have a polynomial here. Okay, but this polynomial are with real coefficients. Every coefficient is real number. Okay, so this polynomial, okay, this polynomial, every coefficient with are real numbers. Okay, A's leading coefficient is a real number, real number, real number, real number. And this is one example. Okay, this is one example. Real number. Okay. And if the complex, okay, and if the complex number C is a 0 of P, then okay, the conjugate of P, the conjugate of C, which we mark it as C bar. Okay, we put a little bar on top of it. Is also a 0 of P. This is a very interesting result. What it tells us is that if we have complex, if we have real number coefficients, the zeros will show up in pairs. Okay, so if one complex number is a 0 for the polynomial, its conjugate is also, like in here, right? We have 1 0 I and we have a negative I, it's also the 0. So the conjugates show up in pairs. Conjugate factors show up in pairs. Finally, okay, linear and the quadratic factor theorem. I said every polynomial with real coefficient can be factored into a product of linear and irreducible quadratic factors. With real coefficients. What does this mean? Right? In this particular example, right? If I want to have a complete factorization, this is a complete factorization, okay? It's a real, this is a polynomial with real coefficient. But then if you say, no, I don't want to complex factors, then what will happen? If we don't want, okay, so this is a complete factorization. Okay, this is complete factorization. If you say, I only want a real number factors, then what we have is that we're going to have some linear factors. And we also have to bring back that x squared plus 1. X squared plus 1 is real factors. Okay, with linear, okay, factors with real numbers only. But in this case, you will not only have linear, you also have irreducible quadratic. What is irreducible quadratic? What's irreducible quadratic? Any quadratic, okay, ax squared plus bx plus c, okay, this is a quadratic. We know that there's a discriminant, right? Discriminant is b squared minus 4ac. Okay, b squared minus 4ac could be positive, 0, or negative. If it is negative, that is called irreducible quadratic. If this is true. Okay, so that's irreducible quadratic. And in our case, x squared, for x squared, right? Example, right? In the case of x squared plus 1, obviously it is irreducible quadratic because we have a equals to 1, b equals to 0, c equals to 1. And the discriminant is b is 0, a is 1, c is 1. And that's going to be -4. It's negative. So x squared plus 1 is an irreducible quadratic. Okay, finally, if we only want to handle factoring in real number, the best we can get is some linear factors and some linear irreducibles, some quadratic irreducibles. Okay, let me say it again. If we factor a real polynomial, meaning the coefficients are real numbers. Okay, the best factor form we can get are some linear factors, sometimes with multiplicity, and irreducible quadratic. So that's what we're getting here. So this is the example that we have seen here. There are plenty of examples in any algebraic, probably college algebra text or rational, or I would say pre-calculus text. So if you like to practice with them, and go find them. I will try to get some examples for you to practice. And I think that's all for this time. Thank you for watching.